Welcome to the HVAC-Engineering-Techie channel. This is the channel where we talk all things HVAC, from engineering design to construction, to equipment, to systems, to controls, test and balance extensively, and system performance. This video is basically about basic physics of temperature and heat calculations. This is the basis of heat transfer and how HVAC systems basically work and what is the parameters. So these videos are intended to provide basic education so that the technician can advance in their career. So let's get started. But before we get started, I'd like to ask a big favor. Would you mind subscribing and on the button down below, hit the button down below to subscribe and to hit like. This absolutely free, costs you absolutely nothing. I'll never bug you. It's just that Google uses that to evaluate this video. So I would really appreciate it. It helps me in continuing to upload these videos, and I have a lot of them to go before we get through the entire subject. So I'd really appreciate it. Let's get started talking about basic heat and temperature. All right, let's start by talking about basic heat. So basic heat, the definition of heat in the IP units, which is what we use in America, is a BTU, and a British thermal unit is defined as the amount of heat necessary to change the temperature of 1 pound of water by 1 degree Fahrenheit. BTUH is a BTU per hour of heat transfer. So basically, BTU is heating up a pound of water, and if you do it by 1 degree, that is 1 BTU. So temperature. There are several different temperature scales, and basically the two used around the world is the Fahrenheit scale is used mainly in the U.S., and centigrade scale is used other places in the world where they use the SI scale. Now, SI is reported as being easier, but in reality, there are some issues, and we've run into them before, trying to convert between the two. So basically, in America, we use a Fahrenheit scale, and the Fahrenheit scale is used in America, as I said, and the Celsius scale is used elsewhere. And the differences is that the Fahrenheit scale goes from 32 at freezing and a 212 at heating, about boiling, and that basically is 180 steps, 180 degrees. But on the Celsius scale, 0 is freezing and 100 is boiling. So basically, we have 100 units on the Celsius scale and 180 on the Fahrenheit scale. And the reason that's kind of important to know, that 1 degree on the Fahrenheit scale does not have as much heat as 1 degree on the Celsius scale. So a lot of times in controls, when we're talking about a sequence, we're using 1 degree as the discriminator. They're not the same. So you got to understand that things can happen differently if you're converted to Celsius than Fahrenheit. So there is a difference there, and you have to understand what those are. Temperature. Now, there are scientific temperatures ranges, which is the Rankine system and the Kelvin system. And these are systems used for scientific work where they reference absolute zero. You know, when we reference freezing, that's not absolute zero. That's just the temperature at which water converts to ice. Absolute temperature is much, much lower than that. So in the Fahrenheit scale uses the Rankine, and the Celsius scale uses the Kelvin. Now, Rankine equals 1 degree Fahrenheit plus 459.67 degrees. That's how cold it is. It's really, really cold down at the bottom there. Kelvin is C plus 273. So those are the formulas for scientific. Most of our calculations, we don't need this number, but every once in a while we'll have one that's dealing with atmospheric conditions where we have to use the Rankine scale. So basic temperature. The Fahrenheit scale, now there is a way to move between Celsius and the Fahrenheit scale, and this is the formula. So there is a formula, it's exact. We'll do that. Another way, of course, is to put an app on your iPhone or your cell phone that allows you to do that automatically. It's what I do. It's easier, but this is the formula. So to convert Fahrenheit, or to convert Celsius to Fahrenheit, you take 9 divided by 5 times the Celsius degree plus 32. And that is how the Fahrenheit, the Celsius can be converted to Fahrenheit. And Rankine, of course, I said before, it's Fahrenheit plus 459.67. So that's the formula to convert it. Now, you can also do the other way. You can convert a Fahrenheit number to Celsius, and the equation is similar. It's 5 divided by 9 times temperature F minus 32. So that puts it into Celsius condition. So you can transfer back and forth by these equations. They are exact again. And then to find Kelvin temperature, it's the temperature in C, or centigrade, plus 273. So that's how we convert back and forth with temperature. All right, temperature of air. Now, air has different properties, and one of them is sensible heat. Sensible heat is the energy required to change the temperature of a substance with no change, no phase change. So in other words, if you have a piece of steel and you heat that piece of steel up so it raises temperature, what's happened there is a transfer of sensible heat. You take a phase change from ice to water, that's not sensible heat. That's another kind of heat, and that's latent heat. Now, sensible heat is a heat that you can feel. So if you go out into the sunshine or out into a hot area and you feel the hot air on your skin, you're feeling the sensible heat in the air. There are other kinds. Now, latent heat is the amount that is hidden, meaning it occurs without change or detectable temperature, which all means a person cannot feel latent heat. Latent heat is actually the heat of the moisture in the air. It's also the heat when air from water goes from liquid to steam, and when water goes from liquid to ice. That's latent heat change. You can't actually feel it. Now, you can feel the results of latent heat. So if it gets real humid outside and the water in the air has temp heat in it, you feel its effect. You don't feel it directly, but you can feel its effect. And of course, what you're feeling is the body's mechanism to deal with heat is to sweat and have that evaporate. And at high humidity levels, it doesn't evaporate. So you feel the effect of that, but you're not feeling latent heat directly. So total heat is the total of the two. It's the sensible latent heat, and these are the three conditions of heat that we work with a lot. And psychometrics is a science of water vapor and deals with the properties of moist and dry air. Now, dry air is really easy. Moist air is when things get to be problematic, and that's why we have weather. Weather is all about moist air, not dry air. So basically, these are the three heats that we deal with every day in working with air conditioning systems. Now, there's different kinds of heat exchange. And radiation is the energy of heat that is transferred directly, radiated by heat waves, and the heat surfaces in the paths. So you have a heat wave coming from the sun or coming from a fire, coming from a hot plate. It radiates out, and it does not actually heat the air it goes through. It heats the material that it strikes. So when you're in a room and the sun's shining through the window, it's not actually heating the air, it's heating the things in the room, including you. If it shines on you, it heats you. So that's radiated heat. That's one kind. The other kind is convection. Convection is the energy of the heat that is transferred from one place to another or from one substance to another due to movement of a fluid. So the fluid can be air, water, steam, or refrigerant gases. Convection can be from natural flows or forced by a fan or pump. The amount of heat transfer depends upon the temperature difference, the velocity of the fluid, type of fluid, material conductivity and size, shape and surface conditions of the surfaces of the heat exchange material. So convection, that is when we blow air through a coil or we blow water through a heat exchanger, we're using convection to transfer the heat. The third type is conduction. And conduction is the energy of heat that is transferred from a warmer object to a colder object when both objects are in direct contact. The amount of heat transfer depends upon the thermal conductivity of the materials of both objects. And conduction is how temperature gets through walls, through solid wall. When the sun shines on the outside, it heats it up, and the heat slowly moves through the wall depending upon the value of the insulation and gets to the inside, and that heat is conducted heat. These are the three different types of heat that we are trying to combat with or move around with HVAC. And it is important to know the difference because you have to deal with them differently. These three types of heat offer different challenges each. So we have to know radiation, convection, and conduction. Okay, basics of heat. Heat always flows from hot to cold. It can never flow the other way. Now, cold can affect heat by drawing heat away from it, but it never flows the other way. And the reason is to get heat, to get hotter requires energy. To get colder is actually the removal of energy. So entropy detects, we always go down, never up. Unless you have a system that's going to put more energy into it, you get hotter, but basically it's still, the energy is hotter than what you're doing to get it to rise. So heat, it always flows from hot to cold. Heat exchanger efficiency is based upon the arrangement of the heat exchanger, the differential temperature, the amount of flow through the fluid on both sides, laminar turbulent flow. Turbulent flow actually can move more heat than laminar flow. In laminar flow, the different flows kind of insulate each other from each. In turbulent flow, it mixes them all up, so you get a more uniform temperature across that. And as you work on HVAC, you'll see where manufacturers will put turbulators inside tubes of a chiller or something like that to get better heat transfer off the surfaces. The type of fluids and their specific heat, how well they transfer energy, area of the heat exchangers, and surface and the material emissivity. Emissivity is basically how shiny or how smooth the surface is. It detects whether it bounces temperature off or whether it absorbs it. All right, now we have different types of heat. Go back to the sensible heat. We have an airflow equation for sensible heat. Now, sensible heat, these equations are based on some standards. So the sensible heat equation, this is called a simplified equation. It works most of the time if you have standard conditions. And standard conditions are 70 degrees at sea level. So it's perfect for standard at sea level. Now, if you go up in elevation, the equation does change as the density of air changes. And if you go up a lot in temperature. Now, if you go to 75, it's minuscule. It will never make a difference. But if you go to 140, it has changed. So basically, it's Q, which is BTU, basically, equals 1.08 times flow times the delta T. Delta T is the temperature difference. And this 1.08 is created from the sensible heat of air at 0.2403 of BTU per degree of a pound of air at 6 times 60 minutes times the density of air, which is 0.0749 at 70 degree temperature. So that's where that 1.08 comes. And you can use it most all the time unless you have non-standard conditions. So this is 1Q equals a BTU per hour. Flow is airflow is in CFM. And delta T is the difference between the entering and leaving air of the coil. And it's in temperature Fahrenheit. So actual sensible heat, the real formula, this is what that is derived on, is the BTUQ equals 60 times the sensible heat times the density times the flow times delta T. So it's the same formula, but we've used the exact values of sensible heat and density. It's just easier to use this one when you know you're around general conditions. So sensible heat is the specific heat of the air. D is the specific density of the air. SV is a specific volume of the air, which is the reverse of density. So specific volume is the invert of density. So that's good. That's how you can always find the specific volume. You don't really need to go to a psych chart. Got the density. Just divide 1 by the density and you get specific volume of the air. Flow of air in CFM. Okay, let's look at sensible heat. There's the definition again, and that's the sensible heat is 2403 and the density is 0.0749. And that equals 1.08. So we know what that is. So if you take this 60 times 2.4, you come up with 1.0799. And of course, it rounds up to 1.08. Okay, there is a little bit of a problem. When you go out and research how all these were created, you'll find some of the original authors used different standards. especially in a Celsius system. They use 59, 69, or 70 degrees. I don't know why. Whereas where in the Fahrenheit system, we use pretty much 70 degrees everywhere. But you need to be aware of that if you're really doing some research or something that's something real specific that needs to be very accurate. You might need to worry about that. Here's a chart of the specific heat of air at different temperatures, and you can see this is the IP version. This is the ISI version, and here's the actual temperature, and here's the temperature C. So you can see that at right around this 70 degrees, we get the numbers we're familiar with, but if you get up to 140 degrees, you can see the number has changed. And then this is density, and density changes a lot. So this is the 70 degrees at sea levels. That is the 0.0749. But if you look at it 6,000 feet, it's a lot different temperature. So the one thing that is important is that you always use the temperature of the air you're actually measuring when you're using these calculations. If you're using a formula and you're changing the standard air, in other words, if you go to 6,000 feet and it's 40 degrees outside and you're dealing with air on the inside, you're not having any outside air in the equation, then you need to use the temperature you're actually measuring. Just because it's 40 degrees outside, it doesn't mean that's what you're using if you're measuring inside air at a different condition. So the density of air at 6,500 feet at 40 degrees is 0.0625, at 70 degrees is 0.0589. So that interpolates to 60 degrees. You can interpolate between the two to 0.061 if you want different temperatures that are in this chart. Okay, I already said that. Okay, sensible heat exchange. Let's do some examples, see how easy this actually is. So what is the total sensible heat of a cooling coil with the following conditions? CFM 1589 and the differential temperature 20 degrees. The reason I use these weird numbers is I also do this for SI, and I try to make them so that they're whole numbers on the SI scale also. So that's why the weird numbers on CFM. So the formula is Q times 108 times flow times delta T. And so in this equation, it's 1.08 times 1589 times 20, which equals 34,322 BTUH. And for 1,589, which is basically a 4-ton unit, 34,000 of sensible heat is reasonable. Now, the one thing you need to realize is that a system can never have, let's say you have a 4-ton unit. This one here would be a 4-ton unit, and it's got 48,000 BTU. Well, that unit can never do 48,000 BTU load with just sensible heat. It will have some latent heat in there, so it has some room for that. But it is important to know that on a unit, sensible heat always takes precedent. So if you have a coil that needs 40,000 BTU of total heat, and you have 34,000 sensible heat, but you have more latent heat than that, it won't do the latent heat. It will do all the sensible heat and a little bit of the latent heat. And this is why systems have humidity problems in the space, because they don't have enough latent heat capacity of the coil. So you have to be careful when you're sizing coils or whatever, that to make sure the sensible, you make sure total temperature is ready, but you also make sure the coil can actually do the sensible load you require. If not, you'll be in trouble. So example 2, what is the total sensible heat of a cooling coil at 6,561 full elevation with the following conditions? That's 2,000 foot in metric, 2,000 meters. So CFM is 1589 again, temperature is 20, but we're at 6,000 feet. So this time we're going to use the real formula, not the simple formula. So we got 60 times the sensible heat times density times the flow times delta T. So it's 60 times 0.2403, which is specific heat of the air, times 0.0601. That's what I looked at before, where I showed how we interpolated from the table, times 1589 times 20, and that equals 27,538. That's also reasonable because air at altitude has less density, so it carries less heat. Heat is carried by the pounds of air, not the CFM of air, but the pounds of air. And since there's less pounds up there, there's less heat. So the very same conditions at sea level is 34,000 BTU, the very same conditions at altitude of 6,000 feet are basically 27,000 BTU, so less. So those are reasonable numbers. So now we're going to talk about latent heat exchange. It has similar formulas to sensible heat with, of course, different factors. So the latent heat of airflow equation is, this is a simplified version, Q or BTU equals 0.68 times flow times delta grains. Grains is a unit of moisture. So this 0.68 equals 60 times density at 7 degrees. The density could be 1 over specific volume. Remember, they're reciprocal. At 70 degrees at 50% times 1076 over 7,000. 7,000 is the number of grains in a pound. And the 1076 is the number of grains it requires to condense 1 pound of moisture. We'll get to that definition in a second here. So flows in CFM, delta grains is in grains. The actual equation is 60 times density, or 1 over specific volume, times 1076 divided by 7,000 times flow times delta grains, which D is a specific density, or at 50%, or 1 over specific volume. And AG is the humidity ratio in grains of moisture per pound of dry air. 1076 is the heat required to condense 1 pound of water. 60 minutes is 1 hour for unit conversion. Okay, definition: standard conditions for moist 60 degrees at sea level. Specific heat of 0.243 and density of 0.0749. 0.68 times flow times delta G, where the 68 is 60 times 1 over 13.5, which is a specific volume. And the reason I'm doing this is because this 13.5 is directly off the psych chart, and it's exactly correct. And that number is slightly different than this times 0.99. Very close, but slightly different. So this is the exact number. And that times 1076 over 7,000, which equals 60 times 0.07407 times 0.1537, which is 6.682 or something like that. But it rounds to 0.68. And that, again, is the amount of heat to evaporate 1 pound of water, or condense 1 pound of water, same thing. This is a specific heat table, where this is the IP units, our units. This is the SI units. This is the temperature in Fahrenheit. This is the temperature in Celsius. And this is the table for standard densities. And this is dry air, not moisture. If moisture, you got to multiply these numbers times 0.99. I'm sure that's not terribly exact, but that's the way they do it in this table for this. So if you want to, for HVAC, if you want to get a little tighter, just use 1 over 13.5, which will be pretty good. So now here's how you interpolate it. So the density of air at 50% relative humidity at 70 degrees is 0.0749 per the table. And per the instructions, if it's moist air, you multiply times 0.99, and that equals 0.074151. And then if you want to interpolate the table, density at 6,500 feet is 0.0625. At 40 degrees, at 70 degrees, it's 0.0689. If you want it in between 60 degrees, you can interpolate those tables, and it comes up 0.0601. And we're going to use that in the examples here in a minute. Okay. And remember, these all apply to the temperature of the air you're actually measuring. In other words, you're inside a building and you're measuring 70 degree air and it's 20 degrees outside, and you're not doing outside air, then you need to use a 70 of the temperature of the air you're actually measuring. Okay, latent heat example. Let's do an example. What is the latent heat of a cooling coil with the following conditions? The altitude sea level, CFM is 1589. Delta grains is 15.44. And here's how I got the delta grains off my app. The inlet conditions were this, to give me a humidity ratio of that. Outlet conditions were 5854 with the humidity ratio of that. You subtract one from the other and you get the delta humidity ratio, which is pounds of water per pounds of dry air. Multiply that times 7,000, turn it into grains, and you get 15.44. Excuse me. That's how you come up with that number. So the formula again is 0.68 times CFM times delta G. So 0.68 times 1589 times 1544 is 16,683 BTU. So that's the amount of latent heat in this particular airstream. Example 2 is what is the total latent heat of a cooling coil with the following conditions, which is sea level 1589 is exactly the same, except this time we're going to use the other formula just to see what the difference is. So 60 times D times 107,607,000 times CFM AG, and it equals 60 times 0.074151, which is that number multiplied times 0.99 times 0.1537, which is 10,076 divided by 7,000 times the CFM of 1589 times the grains of 1544. Come up with 16,776. Not exact, but close. 100 BTU is really close. So we wouldn't worry too much about that. And the reason they're not exactly the same is because of these factors we're using are from rounded numbers. So it won't be exact, but it'll be close. Example 3, what is the total latent heat of a cooling coil with the following conditions? Altitude of 6561, CFM of 1589, delta grains of 1544. Again, density of that, 0.0601. So it's 60 times density times 107.6 per thousand. Get tired of reading the same equations over and over. So it would be 60 times 0.0601 times 0.1537 times 1589 times 1544, which equals 13,597. And you see that that's less because remember the high altitude air is less dense, so it carries less heat. So those are the how to do latent heat exchange. Total exchange, simple formula is 4.45 times flow times delta H. And 0.45 is 60 times density at 70 degrees at 50% relative humidity. Q is a total heat in BTU per hour. Flow is CFM. And delta H is the differential enthalpy between entering and leaving air of the coil. So again, you find enthalpy by either off psych chart, which we have a video for that, by the way, when you get to that, or you can use an app. And I prefer app. The psych chart you use trying to figure out what's going on, but to know these exact numbers, I guess the machinist in me likes the numbers to be a little bit more accurate than you get off a psych chart because they're iffy, you know, plus or minus a delta, a decimal, and I prefer to be more accurate than that. So the actual heat formula is 60 times D times flow times delta H. Really not much difference in this, just you have to know the density of the air. So total heat of BTU, 60 minutes is the hour. D is the specific density of the air, flow of air in CFM, and the differential enthalpy. So let's try a couple examples here of this. Okay, now we're going to talk about where we got the 4.45. So it's 60 times 0.0749, which is 4.494. Yeah, you round it off, you get to 4.45. All right, so there's the two tables again, same two tables, and we use them the same as we did before. This is showing you where the two are. Okay, so let's look at total exchange. Example 1, what is the total heat of a cooling coil with the following conditions? Here's our 1589 CFM again. Our delta enthalpy is 7.32, and here's where it came from there. So our entering condition was 78.65. Exiting conditions were 58.52, and that means a difference of 7 that you subtract one from the other, 7.31 BTU per pound in total enthalpy. And total enthalpy is actually total heat of enthalpy. So we'll look at that. So Q145 times flow times delta H equals 4.45 times 1589 times 7.32, which equals 51,760. Now, it's not exactly, if you add up the sensible and latent and the other, it'll come up slightly different numbers. And again, that's because of the rounding of the decimal places, but they're close. They're not. So if you did the others like we did before, you get 51.05, so like 600 BTU apart. It's not significant, actually. For HVAC, to be exact is hard to do. So we just need to be close enough to what we want it to do. We want to make sure you have enough cooling or heating to actually make the space comfortable. But this is the values of how you calculate those heats. Example 2, what is the total heat of a cooling coil at 6,561 foot elevation with the following conditions? 1589 again, a delta enthalpy of 7.32. So 60 times D times flow times delta H equals 0.0589 times 1589 times 732, which equals 41,000 BTU. So you can tell again that the heat holds less air, so the total is less. So basically, remember the total heat equals sensible heat plus latent heat. If you did this before, it was 40,932. So again, we have a few hundred BTU difference, but not too unreasonable to be able to affect the calculation. I've always, by just habit, because I have to know what the sensible heat is, I always calculate sensible, latent, and add them together. It's slightly higher than total calc, but that's how I've always done. And that's basically for heat and temperature. Short system. I hope this helped. See you on the next one.